Before we discuss the losses that are associated with cables, we will discuss the leakage current. Okay, so we have seen that there exists capacitance. Now we also know that there will be some resistance component. So why there is a resistance component? If you consider this diagram, this is the core and this blue color here is the boundary of the insulator. That means this entire region is the insulator. So forget about the red lines for now. Okay. Now what is happening? Where the leakage current is coming into picture and the resistance, the insulator will allow some current to flow through it. Even though the current amount is very negligible, it will still be present. Okay. Now there is a potential, the core will be at an operating potential, and this, which is the metallic sheath, it will be at ground potential. So the voltage across the insulator is V, let us say operating voltage V. Okay. Then the current will be flowing in this direction, all through this direction radially. Okay. So you can take the leakage current to be like this, radial direction. Now the insulator is a bad conductor, so it will offer resistance, a very huge resistance. Okay. So that is nothing but the resistive component. So we will try to find out what is that resistance for the leakage current. Okay. For that purpose only we have considered this red lines. We have considered a ring of elementary thickness. Okay. So this thickness is dx we will take, and the distance of the ring from the center is x. Now we know the expression for resistance. This is rho L by A. This is in general. Now for this elementary ring that we took here, we will find the resistance only because of that elementary ring. Okay. So resistance of the element of thickness dx. So this we will take as dr. This is going to be resistivity, anyways it will be rho. The area of cross section, what will be the area of cross section? So the cable is basically a cylinder, right? And the current is what? It is flowing radially. Then what will be the cross section? The area that is perpendicular to it. So that is going to be the curved surface area of the cylinder. Okay. So that we can take as 2 pi x into L, right? Because the element has a radius x and the length we are taking some L. Okay. Into what is the length? The length that it is traveling is dx, right? So this is dx. Now we have to integrate x from small r to capital R. Okay. So r is equal to, x is equal to small r to capital R, rho by 2 pi x L dx. So you are going to get rho by 2 pi L ln r by r, where L is length of the cable. So one important thing that you can see here is the insulation resistance is inversely proportional to the length of the cable. Okay. The normal resistance to the flow of normal current, right, that is proportional to the length, but insulation resistance, the current direction is different. Okay. You can see it is radial to the core. So in that case the resistance will be inversely proportional to the length. Okay. So this point, remember, it's important. Now we will see what are the losses. So if this is the core, then you have a resistance and a capacitance as well. So you can see that the leakage current, it is going through a parallel combination of resistance and a capacitor. Okay. So this if you take as I, which is the leakage current. Okay. And what will be the potential across this? It is the operating voltage V. Okay, so you can see that the current will be a leading component. There is going to be a phase difference between the voltage and current, right? So voltage, if you take as the reference, this is V, and I is going to be like this. This is the power factor angle. Okay, so if you draw the horizontal component, what will be the horizontal component? Through the resistance. So the current through resistance is V by R. So you can take as Ri to show it as the insulation resistance and capacitance of insulation. Okay, and similarly the vertical component is going to be the current through the capacitor. So this is going to be j omega Ci into V. Okay, now this angle here 90 minus phi, that is the delta. Okay, and tan delta is called as the loss tangent or dissipation factor. What is the value of tan delta? This is going to be the length of this line divided by the length of this line. Okay, so here tan delta is equal to V by Ri divided by omega Ci into V. So what will this be? 1 by omega Ci R, Ri. Okay, so this is the dissipation factor or the loss tangent. The losses are sometimes expressed in terms of the dissipation factor. Okay, so there are two kinds of losses in the cable. The first loss is the dielectric loss. This is all type of losses. So the first one is the dielectric losses. So this is due to the presence of leakage resistance, which is nothing but the insulation resistance. Okay, so what will be the losses? The current, which is V by Ri square into Ri. So this is equal to V square by Ri. This is the dielectric power loss per phase. Okay, now instead of Ri, you can also write in terms of the dissipation factor, right? So what is R1 by Ri? Omega Ci into tan delta. So this is V square omega Ci tan delta. Okay, you can further express omega in terms of the frequency 2 pi f. So this is the dielectric loss. The second kind of loss is the sheath loss. So the cable, the core is going to carry alternating current, right? When there is alternating current and there is a metallic conductor nearby, the metallic sheath is a metal, right? It's a conductor. So what will happen when it is in the presence of an alternating current? It is going to experience a time varying magnetic field. When there is a time varying magnetic field, current will be induced. Okay, so the pulsating magnetic field produced due to the alternating current in the core induces current in the sheath. Okay, so this is termed as, when there is current, there will be some power is being used up, right? So that is called as sheath losses. So this is very small in comparison to the dielectric loss, very small in comparison to dielectric loss.